Analyzing rational functions. Rational functions have the form y equals p of x divided by q of x, where p of x and q of x are polynomials. So these are the ones where you're dividing something by something. The non-permissible values, which we talked about in 2 units last year, the NPVs, become asymptotes. Do you remember that word from last year? A little bit? Asymptotes. So we're going to look at the different shapes of rational graphs. We looked at most of these last year. We're going to add a few new ones in. We're going to categorize them into 1 vertical asymptote graphs, 2 vertical asymptotes graphs. Turning the page for a second, the no vertical asymptote graph, and then this new one which is called graph with holes. So a 1 vertical asymptote graph, typically it's on the y-axis, but it doesn't have to be. Anyone remember what these ones were called? Remember, mathematicians were not creative people. Yeah, these were the volcano graphs. So you have a piece on the right that approaches the asymptote and a piece on the left that approaches the asymptote. Volcano. Then we have 2 variations of volcano. So again, just 1 vertical asymptote for both of them. The first variation of volcano is when 1/2 is above the x-axis and the other half is below the x-axis. So I'm going to put it in quadrant 2 and 4. I could put it in 1 and 3. And we'll talk about later how do you know which ones it is, but one piece is up and one piece is down. Doesn't look like a volcano, but we still call it volcano because it's got a 1 vertical asymptote. The second variation, or the third 1 vertical asymptote, we did not show you last year because it would have freaked you out. It also has what's called an oblique asymptote, which just means slanted. So this is called oblique asymptote. And what happens is you get one piece of the asymptote approaching the vertical, or one piece, sorry, of the volcano approaching each of those asymptotes. So it crosses through the x-axis, and the other piece will be on the other side. So kind of like the second graph, just stretched out a bit and with a different asymptote. And they don't have to be on these sides. They could be on the top and the bottom spaces. Just depends where the base graph is. So we categorize these all together. We call them 1 vertical asymptote graphs, or we call them volcano graphs. The 2 vertical asymptotes graphs, so we typically have one on the left and one on the right. You saw the first one last year. You did not see the second one. The first one is where you end up with volcano on the very left and volcano on the very right. And then you get a parabola on the other part of the graph in the middle. So it goes volcano, parabola, volcano. Anyone remember what we called that one? My favorite name of any graph in the entire world? Sad clown face. That's about as creative as mathematicians get. A variation of sad clown face, which we didn't see last year, starts with the volcano piece on the bottom. We get a swoop going through the middle. And then the second volcano piece at the top on the right. So it's a variation because the two volcano pieces are on opposite sides of the x-axis, and instead of a parabola, we get a cubic in the middle. Okay, so from last year, what I've added in is this oblique graph you didn't see last year, and this swoop in the middle graph you didn't see last year. These three you saw last year. A no vertical asymptote graph. Anyone remember what that one was called? So we had volcano, we had sad clown face, and we had speed bump. It's the one that approaches the x-axis, gets a little bump somewhere in the middle, and then approaches again on the right. Speed bump. The last one you didn't see last year, so again, you saw kind of half of these, this one's brand new, is you end up getting a little hole somewhere. And it doesn't have to be the first quadrant, it can be anywhere. And then you get a function around it. Could be a line, could be a parabola, could be a volcano. I'm just going to do a linear for the first one. So you get a line on the left and right. We call it graph with hole because we're that obvious. It's a graph with a hole. And again, it doesn't have to be a line, it can be a parabola, it can be volcano, it can be any one of our graphs. You just end up getting a hole in the middle of the graph. Yes, ma'am? It's just a hole. It's just a spot that doesn't exist. So instead of an asymptote, where there's all those values that don't exist, there's just one coordinate point in the middle of the graph that doesn't exist. And I'll show you in a second how to find it and what it means. It's just a hole. So we're not actually going to do any graphing today. What we're going to do is the theory behind it. We're first going to look at how do we find vertical asymptotes. Then we're going to talk about horizontal and oblique asymptotes. So horizontal we talked about kind of last year. It was the one I kept saying, you know, it's there, but we're not supposed to talk about it to grade 12. Well, now we're officially going to talk about it. And I'm going to add in this oblique asymptote that's new. Then we're going to solve rational equations graphically. So I'm just going to throw in this last little piece because it follows from what we did last class. We're not doing any graphing. The graphing is going to come next day. This is just the prep in order to be able to graph. You're going to need paper because I didn't leave your room. So we're going to start with how to find vertical asymptotes, and you've done 90% of this last year. It's the same thing as finding restrictions or finding NPVs. Step number one is you factor anything. Factor the top, factor the bottom, anything that can be factored, you factored. Here's the trick between a hole and a vertical asymptote. If the binomial in the numerator can cancel, what it tells you is that there's a hole in the graph. If the binomial cannot cancel, it's a vertical asymptote. And I'll explain more what that means when we go through the first example. So we factor everything. If something cancels, it tells you that that thing that cancels is a hole. If it doesn't cancel, it's a vertical asymptote. Okay, those are the two choices, hole or vertical asymptote. So again, we're not actually doing the graphing today. We're just going to practice finding this, finding the horizontal, finding the oblique in order to be able to graph next day. So example number 1 says find the NPVs and decide if they are asymptotes or holes. Looking at the top first, can we factor the numerator, x plus 3? How do we know if we can or cannot factor something? How do you know by looking at it we cannot factor it? There's no squared. If there's no squared, it means it can't be factored. It means the top is a linear function, so we're not going to do anything with it. Can we factor the bottom? Yes, it's got a squared. Anyone remember what kind of factoring's on the bottom? What's it called? Kind of. Not perfect squares, but difference of squares. Difference of squares are when you have two terms, they're both perfect squares, and you have a negative in the middle. So we take the square root of x squared, which is x and x. We take the square root of 9, which is 3 and 3. And what do the signs always have to be? Positive and negative. What do you notice about the x plus 3 on the bottom and the x plus 3 on the top? It cancels. What that tells you is that x plus 3 equal to 0 is a whole. And the whole occurs at x equal to negative 3. Did x minus 3 cancel? No, so that tells you x minus 3 equal to 0 is a vertical asymptote. And the vertical asymptote occurs at x cannot be 3. Why do I have a cannot be here? Because that's how we write the equation of an asymptote. That's all this question is asking, is figure out the NPVs and tell me whether they're holes or asymptotes. How do you know if something is a hole? It cancels out. How do you know if it's a vertical asymptote? It doesn't cancel out. Let's look at B. Y equals 2x plus 2 over x minus 4. Factor anything you can. Can we factor the top? Well, it doesn't have a square, but what does it have? Common factor. So what can I factor out of the top? A 2. What's going to be left? Perfect, x plus 1. Can I factor the bottom? Nope, so I'm just going to leave it, x minus 4. Is the bottom a hole or a vertical asymptote? It's a vertical asymptote. How do you know? Because it didn't cancel. And the vertical asymptote is that x cannot be. So in this case, we didn't actually need to factor the top because it didn't cancel, but we need it for something later we're going to do. So I just always do it in this step, cancel the top, factor the bottom. If it doesn't cancel, vertical asymptote. Number C, I guess letter C. X squared plus x minus 2 over x plus 1. Can we factor the top? Okay, this is called product sum factoring. So you're looking for a product of negative 2, a sum of positive 1. Sum of positive 1, product of 2. Offers. Offer of negative 1 plus 2. Let's just check. So negative 1 times 2 is negative 2. If I multiply the x's, I'm going to have 2x minus 1x. When I combine them, what do I get? X. Good to go. The bottom, cancel or no cancel? No cancel, so that tells you it is a vertical asymptote. And the vertical asymptote is where x cannot be negative 1. Go ahead and factor the top. the top becomes? Offer of x plus 3x minus 4. Okay, what about the bottom here? Okay, so can it cancel? Just grab your red pen. There's a rule from grade 10, which you've probably long since forgotten, that says if you want to cancel a minus b with b minus a, okay, so the same terms, but they're backwards, you can cancel, except it's not equal to 1, it's equal to minus 1. And I'll just show you why mathematically that is. What we're doing mathematically is actually factoring a negative 1 out of the bottom. And so if I have b divided by negative 1, what does it leave me? Negative b. And if I have negative a divided by negative 1, what does it leave me? Positive a. And then if I keep the top, and I keep that negative 1 in front, and I just switch the order of the other two terms, what do you notice in binomials? They're the same. That's why it leaves a minus 1. Okay, back from grade 10, I don't expect you to remember. The key is, yes, we can cancel. It's just in front we're going to end up having a negative. And that doesn't affect the whole vertical asymptote thing. It's going to affect the graph later on, though. So can they cancel? Yes. So what does that tell you about the bottom? It's a hole. The hole is going to occur where x equals 4. Okay, so anytime you have where it's reversed and there's a negative in the middle, yes, it cancels. It just ends up being a negative 1 instead of a positive 1. Again, it doesn't affect what's going on here, but it will affect what the graph looks like. Because now you know what's a negative in front of a graph. It's a vertical reflection. So if you miss that, you're going to miss the vertical reflection, which is going to change your entire graph. Show me your thumb so far on holes versus vertical asymptotes. Getting it, kind of getting it, not getting it. Okay, and if you're still here, I'm okay with that, because we're going to practice more when we do next day. Okay, what do we do with both horizontal and oblique? Well, we do what's called analyze the degree of the numerator and the denominator. And just a reminder, that's what vertical or what rational graphs look like. It's just a polynomial divided by a polynomial. Grade 9, you learned about degrees of functions. What is a degree of a function? Anyone remember from 3 years ago? Degree of a function. Yeah. High five to you. Highest exponent means the degree. So if we think of parabolas, what's the highest exponent we see in a parabola? Squared, so we call that a degree of 2. If we think of a linear function, what's the highest exponent we see of x in a linear function? 1, degree of 1. A cubic, which we did in the first unit, what's the highest exponent in a cubic? 3, it's called a degree of 3. So there's going to be 3 possibilities. The degree of p of x is 1 less than the degree of q of x. The degree of p of x is going to equal q of x. Or the degree of p of x is 1 more than the degree of q of x. Here's how my brain remembers it. I say degree over degree plus 1. The second case is degree over degree, so they match. The third case is degree plus 1 over degree. There are other possibilities. We're not going to talk about them. So you could have a difference of 2 degrees. You could have a higher degree on the bottom by 3. You could have a higher degree on the top by 12. We're not going to talk about those. We're going to stick to these 3 cases. Is the bottom is 1 more than the top? They're exactly the same, or the top is 1 more than the bottom. Now, I completely switched these examples, so we're going to cross them out because it's going to confuse you if you don't. And I'll give you new examples. So when the degree of p of x is 1 less than the degree of q of x, an example could be a linear function on the top, x minus 4, and a parabola on the bottom, x squared plus 4x plus 5. Okay, just made those up out of my head. Again, with a linear function, we don't see that exponent, but we know that it's equal to 1. So this is the first situation. You have degree over degree plus 1. The degree on the top is 1. Degree on the bottom is 2. The second situation is they're identical, and this example is fine. So the degree on the top is 2, degree on the bottom is 2. That's case number 2, they're identical. Third one is the top is 1 more than the bottom. So an example, we could have a parabola on top, x squared minus 7, which means we would have a linear function on the bottom, 2x plus 8. And I'm just making up these examples. Okay, what does it mean? If you have degree over degree plus 1, what that tells you is that there's a horizontal asymptote, and it's always y equals to 0. It's right on the x-axis. You have a horizontal asymptote, and it's always on the y-axis, or the x-axis. If it's degree over degree, so the 2 degrees are identical, you still have a horizontal asymptote. However, it's not at the x-axis, and I'll explain what this little formula means when we get down to an example. We call it the leading coefficient of p of x divided by the leading coefficient of q of x. So you still have a horizontal asymptote, it's just not at 0. It's somewhere else, and this little formula will tell you where it is. The third case, when the top is more than the bottom, so degree plus 1 over degree, you don't have a horizontal asymptote, you have what's called the oblique asymptote. And in order to find it, we're going to use something called synthetic division, which I'll show you when we get down to the example. Those are the only 3 possibilities you're going to face. Degree over degree plus 1 is a horizontal asymptote right on the x-axis. Degree over degree is also a horizontal asymptote. It just means it's somewhere else, and I'll show you how to find where it is in a second. The third case, when the top is more than the bottom, degree plus 1 over degree, you have that slanted or that diagonal asymptote, and I'll show you how to find it. Those are the only 3 situations you're going to run into. Again, there's a bunch more situations. We're just limiting you to these 3 so you can practice them. Okay, that's the theory. Let's do some examples. So example number 2 is we're going to find either the horizontal or oblique asymptotes. So we're not doing vertical this time. We've already practiced that. We're just focusing on the other 2. What's the degree on the top? Degree of 1, because it's linear. What's the degree on the bottom? 2. So I call that degree over degree plus 1. And again, if that notation doesn't make sense to your brain, use something whatever makes sense. So some people put p of x over q of x plus 1, whatever makes sense. Some people use words. The bottom is more than the top. You just need to memorize is which case is this? Is this case 1, case 2, or case 3? This is case number 1. And case number 1 says we have a horizontal asymptote, and it's at y equals 0. And I'm going to put the or not equal to because that's the equation of an asymptote. That just tells you when we go to draw the graph, that horizontal asymptote is right on the x-axis. So remember last year I was like, just draw them on the x-axis and I'll tell you why later. That's why, because we only did examples like this last year. We didn't do any of the other cases. Okay, let's look at B. Again, I'm not doing vertical asymptotes, so I'm not going to start to factor because that's not what this particular question wants. This wants us just to look at the degrees. What's the degree on the top? 2. What's the degree on the bottom? So I call that degree plus 1 over degree. And is that case 1, case 2, or case 3? So that tells us we don't have a horizontal asymptote. What do we have? An oblique asymptote. An oblique just means slanted. Okay, this is the part you're going to be like, what is going on? Because you've never seen this thing called synthetic division before. Follow it. The more you do, the easier it's going to become. But at the beginning, you're going to be like, what is going on? So just trust me on this one. I'm going to do an upside down division sign. Like a long division sign. And on the outside, I'm going to say if x minus 2 equals 0, what does x equal? 2. So I'm going to put a 2 down here outside my long division sign. So it just comes from taking the bottom and solving it for 0. Still with me. What I'm going to put up here are the coefficients of the top. And I'm going to start with the x squared, and then I'm going to have an x, and then I'm going to have a number. What's the coefficient of the x squared? Well, it's minus 1. What's the coefficient of x? Well, I don't have 1, so what coefficient would it have? 0. And then the last is the constant, which is 5. Okay, so I'm just going to make some notes because it's our first one. This is because it's negative x squared. The 0 comes from 0x in the equation, and the 5 comes from being the constant. Again, I know when you've never seen this before, this is like, what? Just follow with me. I'm going to drop the 1 straight down and put him underneath that division sign. Then I'm going to multiply him by 2 on the outside. So what is 2 times negative 1? Negative 2. Then I'm just going to add this column vertically. So what's 0 plus negative 2? Negative 2, because we're adding, not multiplying that time. Then I'm going to repeat that process. I'm going to multiply 2 times negative 2, negative 4. Then I'm going to add vertically, and I get 1, positive 1. So again, I'm just going to make some notes where these numbers came from. This was the negative 1 times 2. The negative 4 came from negative 2 times 2. This negative 2 down here came from 0 plus negative 2. And the 1 came from 5 plus negative 4. Again, I know the first time this is crazy. You're going to see once you do it a couple times, it gets really easy where the numbers are coming from. What I care about in this is the first 2 numbers on the bottom. I don't care about that third, and we'll learn why in 2 units from now. All I care about is those first 2 numbers. And what's super cool about this synthetic division is the first number is m, and the second number is b. And what do m and b have to do with anything? Well, that's the equation of the line. So that's where our oblique asymptote is going to come from, because oblique just means it's a line that's slanted. So our oblique asymptote is y equals negative x minus 2. And I'm okay right now if your thumb's at the bottom. I'm okay with that because it's the first example. It's a little funny at first. We're going to do a couple more in a second. This is called synthetic division, which synthetic means like fake because it's fake division because I'm just kind of playing with the numbers. The first 2 numbers are always going to be m and b. I don't care about the third number. He's irrelevant until 2 units from now. But for our purpose, he's irrelevant. It's the first 2 numbers that give me my m and my b. This is why we need to do all the theory before we get to the graphing. See, y equals negative x squared plus 5 over 3x squared. Degree on the top, 2, degree on the bottom, 2, so I call this degree over degree. And you'll eventually have memorized, is this case 1, case 2, or case 3? And we're always like, oh, if it's not case 3, because case 3 is the most amount of work. We're happy when it's the other cases. Case 1, case 2, or case 3? Case 2. So that means there is a vertical or horizontal asymptote. It just means that it's not at 0, it's at some other value. And where the value comes from is the coefficient of x squared on the top divided by the coefficient of x squared on the bottom. That's called the leading coefficient. It's leading because it's the biggest exponent and it's the coefficient that's attached to it. So it comes from the coefficient of the x squared on the top divided by the coefficient of the x squared on the bottom. The number here, even though I don't see it, we know it's negative 1. and on the bottom it's 3. So our horizontal asymptote is that y cannot be negative a third. What that means is it's slightly below the x-axis. Let's just recap because we've seen all 3 cases. Case number 1 is when the bottom degree is more than the top degree. That's our favorite case because it's the easiest. It's the least amount of work. We know that that's y equal to 0. The middle one is when the top is higher than the bottom. That's when we have to do this thing called synthetic division. In the end, we'll end up with the equation of a line because what we're trying to find is the oblique asymptote. The second case is degree over degree, so the 2 degrees are the same, and the value comes from just dividing what's called the leading coefficients, the coefficients of the x squareds. How are we feeling? Yeah, and again, this is okay today. I'm okay with that. Let's do 2 more. Bless you. Bless you again. X squared plus 6x plus 7 over x plus 2. Degree on the top is 2. Degree on the bottom, 1. Which case is that? That's a case 3 because it's degree plus 1 over degree. Yes, I also sigh when we get to case 3. Yes, ma'am. Oh, thank you. Okay, upside down division sign. Number on the outside comes from the bottom and what x is equal to. So if x plus 2 equals 0, x equals negative 2. And I would not normally show this. I'm just showing it for you so you understand when you look back where the numbers come from. I would jump right to negative 2. The number inside comes from the coefficients of the top, and it has to go in order. So the x squared comes first, then the x, then the number. What's the coefficient of x squared? 1. What's the coefficient of x? 6. What's the coefficient of the constant, or the last number? Negative 7. The first number always drops straight down. Then we multiply by the guy on the outside. So 1 times negative 2, negative 2. Then we add vertically. 6 plus negative 2, 4. Then we just repeat the process. We multiply by the guy on the outside. So 4 times negative 2, negative 8. Add the last column vertically, negative 15. I'll just pause there if there's any questions where any of those numbers have come from. Which are the 2 that I care about? First 2. I don't care about the last. Again, he'll become important later, but for our purposes this unit, I don't care about him. What this tells us is the equation of the oblique asymptote is y equals 1x that I don't need to put plus 4. It's the line y equal to x plus 4. Turn and talk. Decide if it's case 1, 2, or 3, and tell the person, how do you know? What case? How do you know? Degree plus 1 over degree. Why are we practicing so many of these? Because they're the hardest. Okay, you tell me. I'll write down whatever you tell me to write down. Well, maybe not whatever. Which, by the way, to the rest of the world, this is how they write the division sign. It's only North America that writes it the other way. So it's actually not upside down to everybody else. I heard someone say negative 3 on the outside. Why? Where does that come from? X plus 3 equals 0. X equals negative 3. Offer of 1, 0, negative 4. Where did those come from? So the x squared, why a 0? Because there's no x's and then the constant. Mm-hmm. 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 You don't need to put these arrows. I just find for visual people, it just helps you remember where the numbers are going, but you don't need to write them. It's completely up to you. Notice how you already got that after 2 examples, right? So again, I know at first it was like, what? What numbers do I care about? First 2, what do they give me? The oblique asymptote. So y equals? Questions so far? Next example, we're just going to put all this together because this is what we need to do in order to graph these next day. The first thing we do is we determine the NPVs and we decide if they're asymptotes or holes. Step number 2 for graphing, we determine are there any horizontal or oblique asymptotes. The third thing we need to do is find any intercepts. What's an intercept? On the x or y-axis. How do we find intercepts? You've been doing it since grade 10. What's the method? So how do we find x-intercepts, for example? Put y for 0, solve for x. How do we find y-intercepts? X for 0, solve for y. So that method hasn't changed. We're just adding it in because when we graph, we need to know some points where this is. So we're just putting all this stuff together. So question number 1. Because I'm left-brained, I always do 3 columns. If you're not left-brained, feel free to put it wherever you want. But my brain thinks vertical asymptotes, horizontal/oblique asymptotes, intercepts. Okay? You don't need to use the columns, it's just how my brain sees it. If you're right brain, I don't know, do these in a line, do them wherever, do them in bubbles, do them around the page, I don't care. How do we find vertical asymptotes? Dead silence, like I didn't teach you this 20 minutes ago. Factor anything you can. If you can cancel, it's a hole. If you can't cancel, it's a vertical asymptote. Can we factor the top? Yep, common factor. Top becomes? Can we factor the bottom? Nope. Can we cancel the bottom? Nope, so that tells you it is a vertical asymptote. X cannot be 4. How do we find horizontal or oblique asymptotes? We analyze the degree. What's the degree on the top? 1. What's the degree on the bottom? 1. So I call that degree over degree. Again, you don't need to call it that if that doesn't make sense to you. And now you just need to memorize the cases. Is that case 1, case 2, or case 3? It's case 2. Is that oblique or horizontal? It's horizontal. How do we find the value? Leading coefficients divided. So the leading coefficient on the top is 2. Leading coefficient on the bottom, 1, which I normally would not write that. I just want you to look back later and see what we did. I would just write this as y cannot be 2. I just don't want you to think later that we just took the top. Intercepts. I always do y first because they're the easier ones. This is where you put 0 for x and solve for y. And you don't need to show that work, because if you look at the equation, everything with an x is going to go. So all you're looking at are the numbers that are left, which is 2 divided by -4. If we reduce it, what's 2 divided by -4? -1/2. So you don't need to show this step. If your brain can see it's -1/2 right away, it's -1/2. I like to write the coordinate just to remind ourselves this is a point, not an asymptote, not anything else. It's a point on the graph. The graph is going to cross through 0, -1/2. So again, just repeat, you don't have to show the work. If your brain can just see it, write it down. If your brain needs to show it, show it. Now I'm going to do the x-intercepts, which means we put 0 for y. I'm going to bracket the bottom, because for some brains it's a little bit easier to see what I'm about to do. How do you get rid of a division by x minus 4? You multiply, so it's going to come up to the other side. And what happens when you multiply anything by 0? It's just 0. So the bottom, in essence, goes away. And it's just because mathematically we've multiplied it by 0. How do I get rid of a +2? How do I get rid of a coefficient of 2? So x is going to equal, almost, negative, right when I bring the 2 over. And again, I just like to write this as a point just to remind ourselves it's not an asymptote, it's a point that the graph is going to pass through. There's all the prep work that we need to do just to be able to graph these the next day. We always have to find the vertical asymptotes, or the holes, the horizontal, the oblique asymptotes, and the intercepts. I know, these are a lot of work, I know. But they're really pretty when they're done. Again, don't feel you have to use the columns. It's just the way my brain sees stuff. Factor anything. If you haven't noticed, we already did this when we did vertical asymptotes. It's the exact same example. That's the offer I heard. Okay. What's the conclusion about the bottom? Can't cancel, so it's a vertical asymptote. X equals, or does not equal, -1. Horizontal and oblique, look at the degree. What's the degree on the top? 2. What's the degree on the bottom? I already hear the size. Degree plus 1 over degree. I feel it too. What goes on the outside of our division sign? -1. What goes on the inside of our division sign? Drop the 1, times by -1. Add that column. Now really, you don't even have to do the rest of it because we know the numbers are relevant. I just want to do the rest because later on we need that number, so just to practice. Y equals just x. Y-intercept. I don't actually sub in. I just go back to here and I say, well, anything with an x is going to go. So what's going to be left on the top? -2. And what's going to be left on the bottom? 1. And what's negative 2 divided by 1? Negative 2. And again, I like to write it as a point, just so later we're not confused. Is it an asymptote? What's going on? It's just a coordinate point. It's where the graph crosses the y-axis. X-intercept. This is why we factor the top even when we don't need to. Because what's going to happen is the bottom is going to go away, and we're going to end up with x squared plus x minus 2. So bottom goes away because we're multiplying by 0. How do you solve a quadratic? Factoring, quadratic formula, completing the square root, which is factoring, and graphing. That's why I factor here, so just grab the factoring right away. Now you can just solve for those two x's. 2 and positive 1. Because when you multiply by x plus 1, what's going to happen with the 0 on the other side? Right, what 0 times x plus 1, it's going to go. So just like we did up here, the bottom goes. And again, these are coordinate points. We have 2 x-intercepts. And we'll find out when we do the graphing next day why. Why do we have 2? What's going on there? Yep. Yeah, there's usually 1 on the exam. So in the grand scheme, it's not that bad. Oop, minus 9. Again, please don't feel you need to do the columns. It's just the way my brain works, but if you can just do it all on one page, do it wherever, I don't care. Okay, vertical asymptotes. How do we find vertical asymptotes or holes? Factor anything you can. Can we factor the numerator? Nope, no common factor, no x squared, nothing we can do. Can we factor the denominator? Okay, what do you know about the x minus 3? It does not cancel, so it's a vertical asymptote. Y cannot be 3. What do you know about the x plus 3? So it's a whole. I don't know why I put a y there. That should be an x. X equals negative 3. Do you understand why 1 is a vertical asymptote and why 1 is a whole? Cancel whole, not cancel vertical asymptote. Here's the piece we haven't talked about yet, is this is a coordinate point that's going to be that little circle on the graph. The problem is right now I don't know where the y value is. I know it's 3 to the left, but I don't know how up and down it is. I need to know that in order to graph it. How do I find the y coordinate of any point on this function? We put x into that number, so we're going to put in minus 3, and we're going to solve for y. So I'm going to take the original function. I'm going to put in negative 3 for every x that I see. So again, this is just to find the y coordinate of where the hole is so I can graph it. The top is, the bottom is, uh-oh. Can we divide by 0? No, that doesn't work in math. Sad face. What do we do then? We panic. Bah! Okay, then we stop panicking, and we think about, okay, there has to be a y coordinate, because I know it's a hole in the graph. We don't know. Thoughts? Make the graph and hope it works out. No, there actually is a mathematical way to do it. Instead of going to the original function, go to the canceled function. So these are going to go because it's a whole. So what I really have left for my function is 1 over x plus 3. Okay? So I showed you that step because your brain is going to want to go back to the original function. The problem is if you go back, you're always going to have that 0 on the bottom. So you want to go back to the canceled function to find the y coordinate. So this now just becomes 1 over negative 3, negative 3. And on the bottom, negative 3 becomes negative 6. So our whole happens to be at negative 3, negative 1/6. So I'm just going to make a note. I call this the factored form. And that's where you need to go to get your y coordinate. Again, your brain's going to want to go back to the beginning. You're always going to get that divide by 0. You're going to panic, then unpanic, then go to the factored form. Now here's something else that I do for my brain, is I know this is a coordinate point, but what I put in front of it is a little hole, just to remind myself when we're eventually drawing the graph that that's a hole, not just a point on the graph. That's an actual hole in the middle of the graph. Again, you don't have to. It's just something visually to remind myself when we go to graph that there's a space there. Oh, holes are a lot of work. Hello. Is it somebody I want to talk to? Who is it? Who is it? Hello. No problem.
Here's a drawing, and then you draw a scale drawing, like,
Yeah.
you know, like it wasn't a quilt project.
Yeah, no, the enlargement, the cartoon enlargement, yeah.
Do you have any of those?
I do, yeah.
Okay. Can I come find you, please?
Yes.
When's your prep period?
3, but I'm not in here. Allie's in here.
Oh, I'll come find you.
I'll dig them out next class and I'll just leave them. Okay.
Thank you. Sorry to bother you, everybody.
You've now had time to ponder. What are you thinking for vertical or horizontal asymptotes oblique? What are you thinking? Degree over degree plus 1. Okay, what does that mean? Ooh, we love case 1. Why do we love case 1? Intercepts. I start with the y-intercept. I just take away all of the x values and I look at what's left. So if I take away the x values, I've got a 3 on the top and a negative 9 on the bottom. And when I reduce those, I get negative 1/3. You don't need to show any work. If you jump right to 0, negative 1/3, that's full marks for y-intercept. Okay? If you want to show the work because your brain needs it, then show it, but you don't have to. X-intercept. I ignore the bottom. Why do we ignore the bottom? Because you multiply it by that 0 and it goes away, so all I'm left with is the top. So x equals. Questions? Proposal. I would